Hey everybody, Matt Morgan here. In this lesson, we're going to talk about the Bohr model of the atom from section 6.2 in the OpenStax textbook. We'll talk a little bit about the scientist Niels Bohr himself, how he had a model of the hydrogen spectrum. We'll talk about the interaction between light and energy levels, and then we'll go over homework problem number 20. Niels Bohr was a Danish physicist and mathematician. He won a Nobel Prize in 1922 for his model that we're about to talk about, connecting electron energy levels and light. He worked with other brilliant scientists like Einstein and Heisenberg. Nope, not that Heisenberg. There's a picture of him with Einstein. So he tried to explain what the spectrum of light looked like when they excited a hydrogen atom and then viewed the light through a diffraction grating. We saw specific lines at discrete wavelengths. So why those lines and why the spacing? Notice there's a large difference between 486 and 656 nanometers, but as the wavelengths get shorter, the spacing gets narrower. So Bohr thought that electrons orbited the nucleus at specific distances, like planets around the sun. Low energy electrons were close to the nucleus, and high energy electrons were further away. If an atom were energized by either heat or high voltage, electrons would move from a lower orbit to a higher orbit. When these electrons fell back to their starting points, then a photon of light would be emitted. That photon's energy matches the difference between the two energy levels. In the last video, we talked about how to calculate the energy of a specific photon. Here, Bohr matches that energy to levels in an atom. No energy is emitted unless a complete jump occurs between levels. There's no half states. So this is based on figure 6.15 in your textbook. So if an electron drops from the second to the first energy level, then a photon of a light is emitted, okay? And h times nu is the energy of that photon. If an electron drops from a higher orbit down to low, notice there's the larger spacing. The photon is still emitted, but this photon has higher energy because it came from a higher energy level. Once again, here's the spectrum. So short wavelength, high energy photons emitted when electrons drop from the high energy levels. The discrete line indicates that there are specific energy levels, nothing in between those. And finally, the high energy levels are closer together than the low energy levels. And so that's how Bohr's model explained the observed hydrogen spectrum. So scientists do what they always do, and they assign numbers and calculations to observations like this. So they've determined that the energy in each level, the energy of the electrons, is defined by this formula. So why the negative sign? Well, the energy of a free electron is defined as 0. And when associated with an atom, that electron has a lower energy than when it's free. So there's a slightly different version of that formula. This is the formula that we see in our textbook. K is a constant, and it was found by experiment. Now, I've always had trouble with what they call empirical constants. They just made a bunch of observations, ran a bunch of experiments, and found that the energy was proportional to these other values by this proportionality constant. It's kind of like Bullwinkle. Hey, Rocky, watch me pull a rabbit out of my hat. But it works. So for us, we just need to know that K is 2.179 times 10 to the minus 18 joules. Z is the charge of the nucleus. For hydrogen, Z equals 1. And that's why you may not see a Z factor in equations like this, because if they're talking about hydrogen and Z equals 1, 1 squared is still 1. N is the energy level that we're talking about. So because we're dividing by the energy level squared, actually, the lower the energy level, the lower the overall energy, because we're dividing by a smaller number. Let's look at homework problem 20. Illustrates this formula a little bit better. So the problem goes, using the Bohr model, determine the lowest possible energy in joules for the electron in the lithium 2+ ion. So we will use the formula that we just saw. There it is. So N equals 1. That's the lowest energy level we can possibly get. Z is 3 because lithium has 3 protons. Also, a side note, the reason they're talking about the lithium 2+ ion is this model only works for single electron species. So a lithium atom with 3 electrons or a lithium +1 with 2 electrons, this formula wouldn't work. Now, let's plug in our values. There's our formula. There's our value for K. Z is 3. Our energy level is 1. A little bit of cleaning up here. We'll square the 3 to get 9. 1's in the denominator. So all we're doing is multiplying K times 9. Double check my math, but that's the number I get, minus 1.961 times 10 to the minus 17 joules. A pretty small amount of energy, but we're talking about a single electron in a single energy level. So the energy is negative because, once again, like we said, the free electron is defined as having 0 energy, and an electron associated with a nucleus has a lower energy than that. And what's lower than 0? A negative number. So that's really the highlight of the Bohr model. Now the text does talk about energy between different energy levels. We're not going to get into that in this course. If you can calculate the energy of a single energy level, that will be good enough. So we talked about that Bohr model, the relationship between light and atomic energy levels, how to calculate those energy levels, and next lesson, we'll tie all this together. We started talking about light. Now this relates light to electrons, and next we go to where we can find electrons in an atom. As always, if you have questions, there's my email address. Office hours Tuesday and Thursday mornings, 9 to 10 a.m. And you can make an appointment to meet if those times don't work for you.